All right, so good morning. Let's discuss this electrostatic potential problem and associated work done when we carry the charge from a point which has a potential due to multiple charges. And this charge, is carried from the point O to point E, and we have to find, how much is the work done. So first understand what is the situation, and then we will get into, the details of how to solve this. See, every charge, this situation is of 4 charges, 1, 2, 3, 4, located at the end of the squares. Okay, so this is a square. These are all point charges. Every point charge has some potential associated with it. Okay, so that potential is given by V, which is a function of distance and is written as K Q by R. Okay, so this is something I think fundamental concept, that if you have a point charge and you want to find the potential at a distance R, for example, okay, from this charge, the potential due to this charge at a distance R, which is in centimeters or meters, is given by this formula. Okay, this is concept number 1 that you should be aware of. Okay, here you don't have a single charge. What you have is multiple charge, 1, 2, 3, 4, and these charges, create a potential here. Okay, at any point. So if you consider the center, the distance of each charge is this, right, which is equal to half the diagonal. So half the diagonal is your R, being referred to. Okay, so this is the R we are referring to, the distance of the point at which potential is to be found out. We know the distance. That is point number 1 that you have to understand. The second thing is, now, this second concept you have to understand is that potential, is a scalar. Okay, so you can add the potential due to multiple point charges just like numbers. Okay, so if you were to write the potential of this charge and then this charge, you can add it like numbers. So potential, which is a function of distance, is a scalar. Okay, you can directly add all the potentials. And be very careful when you solve the problem. Q, is the charge in coulombs, and use the sign of the charge which is given in the numerical. So if it is a minus charge, put a minus here. Do not hesitate, put the minus here, okay? And then you can calculate the potential at a distance R. If this is minus Q, I will put minus Q. So first point, this is the expression that tells you about the potential at distance R from a point charge Q. So if these are the 4 charges, what you have to do is to calculate V1, which is due to this, at a distance which is half the diagonal. If you know this, the square, the side is this. The total diagonal is obviously root 2a. So you can apply a Pythagoras and calculate the hypotenuse. Half of hypotenuse is root 2a divided by 2, right? So you get the half the hypotenuse as a upon root 2, okay? So that's your half the hypotenuse. So you know the distance of each charge because this is a square. The center, this is the center of the square, okay? So all are equal, just remember that. And now what you have to do is to calculate the individual potential. So calculate this potential, comes out to be KQ by A upon root 2. Then calculate V2, I'm calling this as a second charge, and calculate this as KQ, but I'm putting minus Q because I'm using a negative charge, divided by A by root 2. And then of course I can calculate V3, which is again minus KQ upon A by root 2. The reason is of minus sign is because I'm assuming this to be the third charge, charge number 3, and therefore the potential is, carrying the sign of the charge itself. And then you can calculate V4 also, okay, which is plus KQ upon A by root 2. Okay, so you have a sense of, what are the individual potentials. The potential due to this here, the potential of this here, the potential of this charge here, and the potential of this charge here. Now these are numbers, okay, and obviously, the SI units are volts, okay. The potential is calculated in volts. So that's the first thing you have to do, calculate the potential. And you can see, because of symmetry, the positive and negative, the positive and negative cancel. The positive and negative, the potential is at equal distance. If you add all of this, which means you do, V1 plus V2 plus V3 plus V4, what you will get is 0. So likely what you're getting here is 0. And so that means this point, because of point charges located at the end of the square, the potential here is, net potential here is 0. Okay? Now the question is, so first calculate the potential here, the sum of all the potentials. Then come to the point E, okay? Now if you look into point E, you can calculate this distance and this distance also. Now this is A by 2 and this is A. So this Pythagoras applied here will tell you that this distance is A square plus A square by 4 under root, which is root 5 by 2A. Okay, so this distance also. And this distance will also be root 5 by 2A. Okay? If you want to find the potential at E, right, use the same strategy. But this time, look into the symmetry. The distance between this charge and this charge is root 5 by 2. The distance between this charge and the point E, there is no charge here, but you can assume to be a small charge experiencing some potential. But for the purpose of potential, it's just KQ by R. Calculate the potential of this charge here, calculate the potential, and calculate the potential due to minus Q here. So this distance is A by 2 and A by 2. Again, look at the problem. See, these two charges are symmetrical, with respect to this point. So the potential due to these two will cancel here, right? KQ by R, this will be minus KQ by R cancels. Similarly, at this point, the potential due to plus Q cancels and it cancels here, right? So the net potential here also due to these two charges, because it is right in the middle, will be 0. And because of these two charges will be 0. So you can see the potential at O and the potential at E is 0. So you got the potential 0 here and you got a potential 0 here, which means this particular point is at 0 potential and this also is at 0 potential. So if you have a charge which you bring, a fifth charge, for example, you bring a small, any amount of charge, okay? Let's say you bring a charge Q from outside. If this charge Q, is here and you move it from this point to this point, since these 2 points have no potential difference, there is no work done, when you move the charge from this point to E point. So the third concept you have to understand, which is a concept of work done, is essentially the charge Q, which is made to move through a potential difference of V2 minus V1. This is an expression for work done. Q, which is a charge you're moving from one place to another, and it is Q into V2 minus V1. In this case, the potential here is same and the potential here is same, and therefore the work done, essentially becomes Q into 0 minus 0. There is no potential difference that exists here, okay? So which means the work done to move a charge from O to E is 0. Now if you look into F, okay? Now, if you look into F, F is a bit different, okay? F is different because if you see the distance, and I will use a different color this time so that it's clear, this F, would have a potential due to plus Q, and you can use this expression and add the potentials due to plus Q and get some answer here. And you can calculate this distance because, this is your complete A and this is A by 2. So this will become root 5 by 2A using, Pythagoras theorem where this and this are perpendicular and base respectively, right? And similarly, you can find this distance also. Nothing, exceptional about this. And similarly, you can get potential because of this and this charge, these two charges at the point F. Now remember, you will not get a zero value because this point is not symmetrical. The point E here is symmetrical because, plus Q and minus Q have symmetry. Plus Q and minus Q have symmetry. This is right in the middle. So all the potentials get cancelled. But at F, when you do the sum, the potential due to plus Q here, the potential due to this, the potential due to this, and the potential due to this on F, you will get some finite value. Which means, supposingly, you get some value of sum of potentials of all the, point charges to be X volts, okay? So you get this value here. So the question is, what is the amount of work you did to move a charge, plus Q from this place to this place, okay? So you're moving from, place of zero potential to a place which has a potential. Now, it depends what sign you will get. You can get minus sign here or plus sign here. Depends on sum of all the individual potentials. Again, the potential here is zero. You will have some potential here because this is not symmetrically lying. Apply the formula of potential and use Q into V2 minus V1 to get the net work done to move a charge from point O to F. The charge you are moving, from O to F should be given in the numerical. You must know whether this charge is 2, 3, what the charge is, and then you can decide on, how much work will be done using the expression Q into delta V. I hope this helps, and so go through the concept of electric potential and work done, and also try to understand the concept of symmetry because concept of symmetry, helps you find the potentials without even calculating it. And you can see because of symmetry, you got potential here and here to be zero. I hope you found this useful. You can expect a lot of numericals in NEET and JEE pertaining to this concept. Thank you.